Okay, so in the last 2 weeks of the class, actually going to discuss now how to design controllers uh, using frequency response. So we have so far, specifically in the past 3-4 weeks, we have actually become familiar with different types of analysis tools, like to be able to draw, for example, a root locus or to draw body plot as well as Nyquist plot. And we have also become familiar with some other tools, I'm sorry, such as gain margin or phase margin. So, like I say, in the last 2 weeks of the lecture, I'm going to discuss now how to put together some of these concepts and some of these tools to be able to design controllers, or what we call compensators, through frequency response. So I guess, like I said, this is actually going to be the last chapter, chapter 11 of your textbook that I'm going to cover. So most likely I'm going to cover everything that you see in chapter 11. So in chapter 11, the first thing I'm going to discuss is how to improve transient response of, let's say, a closed-loop system by adjusting a gain in the feedback. So now, for example, let's just assume a very simple case. You have this transfer function g of s, which is your open loop system, and so also in the feedback path you have h of s. So really your what we call loop gain is going to be g of s h of s, which is just going to be what we call open, which often we also refer to it as open loop system transfer function. So you also well, I also showed you earlier how if you just include a gain k, which is just a constant in this loop, then how changing that gain can actually can change somehow the stability of the closed loop system. So in particular, if you remember, through both Nyquist plot, body plot, as well uh, as root locus, we learn what kind of range we should adopt for the gain k in order for the closed loop system to become stable if it's unstable, and if the system is stable, how much further you can push the gain k so that the closed loop system still remain stable. And you actually do all this while you only look at the loop gain, which is in this case just k g of s h of s. So now, but again, so far we have only concerned about, or being concerned about, the stability and stabilization of the closed loop system by adjusting this gain k, or basically finding the range for the k. So now the next question is, what if you want to not only stabilize the closed loop system, but also you want to improve the performance? And by performance, for example, you want to reach to a steady state faster, or with let's say less peak, lower peak, or what we call overshoot. So now these are all what we call transient response. So now you want to, just by adjusting this gain k, you somehow want to improve the transient response. So now remember that this gain k, I can just look at this gain k as just what we call proportional control. So you can in fact just take this k out. So instead of this k g of s, you can just have something like this. So I'm just going to, so instead of this, you can just have something like this. So you can still have that g of s, which is already there. And then you can just design a gain here, k. So now the question is, what is going to be this gain k in order to achieve the transient response to, let's say, a step, or so to a step input that you actually desire. So now the first thing I'm going to discuss in this chapter is exactly how to improve the transient response through gain adjustment. So I'm just going to erase some of these things that I just added. All right, so now the first thing I'm going to discuss is to make a connection between this gain k, transient response of the system, and also phase margin that we learn what is it and how to quantify that in chapter 10 using both body plot as well as Nyquist diagram. So now, let's just quantify the relationship between transient response and phase margin for a system. So now, so it turns out that if you have a unity feedback system, which means that here, if your h of s is just unity, is just equal to 1, and your g of s is just omega n squared divided by s squared plus 2 zeta omega n s. So really your closed loop transfer function is going to be a second order, it's just going to be a standard second order transfer function, which is going to be omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. But now if just your open loop system transfer function is just in this form that you see, it can be shown that the phase margin of the system is or can be calculated as this equation that you see. So now this equation actually tells you that for this second order system, the phase margin is just going to be the arctangent of 2 zeta divided by the square root of whatever you see under this square root. Okay, so now if you know the value of zeta, then you would know what is going to be the phase margin. If you know the value of phase margin, you can find the associated value of zeta, which is the damping ratio. So again, so basically here what you see is a relationship between phase margin phi m and zeta, which is your damping ratio. And again, if you remember, there was actually an explicit relationship between the percentage of overshoot and zeta, and that relationship was this. And again, this is actually, so this was actually an equation that was covered in chapter 4. So the percentage of overshoot to a step input would be e to the power of minus pi zeta divided by square root of 1 minus zeta squared. So if you remember, I said that you can either use this equation if you have the percentage overshoot to be able to figure out what is going to be the associated value of zeta, or if you have the value of damping ratio, then you can find the corresponding value of the percentage of overshoot. So you can either use this equation, or there was also a plot that I had shown, and this plot would show you the percentage of overshoot as a function of zeta, and it would actually look like something like this. So I said that you can either use this one or this one. So all right, so now, but now what you have actually seen in this picture or in this slide is that, so let me just get rid of some of these things. So is that basically now there is a relationship between the phase margin and zeta. And remember that there was also a relationship between the zeta and percentage of overshoot. So really there is a relationship between percentage of overshoot and phase margin. So really the phase margin and percentage of overshoot are related. And remember, percentage of overshoot was actually one measure of transient response. Of course, you can have rise time, you can have settling time, you can have a few other parameters, but specifically if you are interested in percentage of overshoot, then that's actually going to be explicitly related to phase margin, meaning that if you know what is the percentage of overshoot, from that you can find zeta, and from zeta you can find the value of phi m, which is the phase margin. And if you know what is your desired phase margin, from that you can find the zeta, and from that you can also find percentage of overshoot. But quite often you know a desired value for percentage of overshoot, from which, like I said, you find zeta, and from that you can find the value of phi m. So now we have seen that, or we have shown that there is a relationship between a phase margin phi m and also the transient response. But now the question was how we can design the controller by, or how we can improve the transient response by adjusting the gain k that we actually had here. So now the next question is, how do we then make a connection between the gain k and either transient response or phase margin? Those two we have actually shown that those are kind of equivalent. So now, if you remember from body plot, if you are looking for a specific value of percentage of overshoot, which is a quantitative measure of transient response, then from that, like I said in the previous slide, from this you can find zeta, and from zeta you can find the desired phase margin. So now let's say you are given a body plot of a system, and but that actually gives you a certain value of phase margin. But in order to improve the transient response, you really want to improve the phase margin, which means you really want to increase the value of phase margin. So in order to reach a desired value of phase margin, which in this case, so now if you remember, phase margin was actually the so to find phase margin, you have to first look at where the magnitude plot crosses the 0 dB, which would be somewhere here, right? And then you have to actually find at the same frequency associated value of the phase, and you have to actually subtract that from 180 degrees. But now, let's say you want to have this much phi. Okay, so now in that case, if you just find the associated value of the frequency, which is actually going to be this omega phi m, and you find the associated value of the gain, so you see that obviously there's going to be this much discrepancy between this gain and the 0 dB line. So you really have to somehow push your body magnitude plot up by this much. So now basically this would give you the required increase in gain. So basically to put everything together I've so far discussed, so to reach a desired phase margin, which is phi m, which in this plot is shown by CD, we need to push, or we need to raise the magnitude curve by AB, because right now it's here, which is actually far away from the 0 dB line by this much. So now if you just push it up, so if you just push the magnitude plot up by this much, then this point is actually going to touch, or just going to intersect with the real, with the 0 dB line at this point. Okay, and so that required increase in gain is actually going to be the associated value of K that you're really looking for. So now what I have done is just to start from percentage of overshoot, related that to zeta. There was a relationship between the zeta and phase margin, so that would actually give you the desired phase margin. Then I would have to come here and find the associated value of omega, or frequency, and then I have to just look at the magnitude plot to see how far is it from the 0 dB line. That difference is actually going to be the required the value of gain that you need to increase in order to reach the desired phase margin, this much, phi m. So the next thing I'm going to do is just, so just going to show you a 4-step design procedure in order to basically adjust the gain to reach the desired, you can say percentage of overshoot, or the desired phase margin. So step 1, so you draw the body magnitude and phase plot. Step 2, you will have to use the 2 equations that I just showed you earlier. There was one equation that would relate percentage of overshoot to damping ratio zeta. Another equation would relate phase margin to zeta. So what you do, you would have to use the combination of those 2 equations to determine the required phase margin. Let's just call that PM, or phi m. So then the next step would be to find the desired omega, or the desired frequency on the body phase plot that would be associated with the desired phase margin. So in this picture, it would be CD. And you would have to change the gain by basically that K by an amount that's actually shown here, AB, in order to force the magnitude curve to go through the 0 dB line at this particular frequency. So you will have to just basically shift it up, so that this whole, if you just shift this up by this much, then the point B is actually going to now become basically point A. So it's just going to cross the 0 dB line. Okay, so I'm actually going to discuss an example here. So this is the same example of the position control system that we have seen before. So the question is to find this gain K so that it would result in a 9.5% overshoot in the transient response to a step input, to a unit step input. And of course, there are some fixed transfer functions that are associated with the physical model of different components of the system, like power amplifier, motor and load, and also the shaft velocity. And the question is how to then adjust this gain K in order to reach or in order to achieve the desired uh, transient response, which in this case is just going to be 9.5% overshoot. So now So now basically your G of S, which is your open loop system transfer function, is just going to be the product of all these four transfer functions. So it's actually going to be something like this: 100K divided by S plus 36, S plus 100. So now one very, very important thing that I haven't really discussed yet is that this is now a, so now actually this is a, so this is now a third order system. So this is not a second order system. So if you recall the equation that I actually showed you earlier that would relate percentage of overshoot to zeta and also would relate phase margin to zeta. So those equations were specifically for second order system or second order transfer functions. But now the question is then what happens for a system like this that is not a second order system, but rather this is a third order system. So if you also remember, we discussed that there is actually a possibility that we could reduce third, fourth, fifth, or even high order system just approximated by, let's say, first or second order system. And if you remember, that would be actually under one condition, that for example, if we want to approximate a third or fourth or fifth or higher order system by second order system, we might, well, we have to look at the system poles and then just figure out and then just see if the complex poles that are associated with the second order systems are the dominant poles, meaning that the other poles are actually further, at least like 4 or 5 times further away from the complex poles, from the pair of complex poles to the j omega axis. So for example, if we have a pair of poles located at -1 plus minus j, the other poles will have to have at least a real components of -5, -6, -10, etc. So that definitely must be further away from the imaginary axis compared to these what we call dominant poles. So if you can make this approximation that the poles or the third or fourth or higher order systems can be actually approximated by this second order system exactly because of the dominancy of this complex or the pair of complex poles, then we should be able to still use those pair of equations that will relate percentage of overshoot and phase margin to zeta. So now let's just make that approximation. So if we assume that we have a dominant complex poles, so now let's just translate this transient response specification here, 9.5% overshoot, into the desired value of phase margin. So now 9.5% overshoot, if we just use this equation, that means the value of zeta is going to be 0.6. Of course, we can either use this equation or we can just use that plot that we actually had discussed before in chapter 4. So if you remember, that would be actually the plot that would relate percentage of overshoot to zeta. But in any case, so now we get the value of zeta to be 0.6. Then if we use the equation that I actually showed you at the beginning of this lecture, that would relate zeta to phase margin. So if we just plug in the value of zeta here, zeta being 0.6, then the phase margin is just going to be 59.2 degrees. So now really this is going to be the desired phase margin. So now if I now plot my body plot, it's actually going to look like this. So this is going to be the magnitude. So actually this is the plot. So this is going to be this is really going to be the plot, not this one. This is the plot. And of course this is going to be the phase. This is going to be the phase plot, and this is going to be the magnitude plot. But now when we're going to draw the body plot, of course we have to fix the value of k to something. So now you can choose the value of k to be anything you want. You can just choose the value of k to be 1, to be 10, to be 100, whatever it is. But and then, you know, like, I mean, just depending on you know, what, like, if the value of k that you actually get is convenient for you or not. I mean you can always change the value of k, but at the end of, so now if you change the value of k, of course it's going to just move this up or down. And but at the end, when you're going to adjust the value of k, it's just going to turn out to be something different. If you had started with, let's say, 2 different values of k in order to draw your body plot before the gain adjustment, but after you make the gain adjustment and you actually combine the value of k that you start with and the adjusted value of gain, you basically multiply the two. Eventually the adjusted system transfer function is going to be exactly the same. So it doesn't really matter what value of k you start with in order to draw your body plot before you adjust the value of k. So here, just for the purpose of starting from 0 dB at this particular frequency, you know, it actually starts with the value of k to be equal to 3.6. So now let's just say with this value of again, this is going to your body plot. So now your desired phase margin, according to your transient response specification, we calculated it was 59.2 degrees. So now, but 59.2 degrees is actually, so it does mean that it just means how far it is from the negative 180 lines, which is going to be right here. So, and of course, it's just going to be negative 180 plus this 59.2 degrees, which is going to give you almost negative 121 degrees, which is going to be somewhere here. And this is actually going to be associated with the frequency of, so that's like between 10 and 20, so that's like kind of in between. So it turns out that that's almost 14.8 radian per second. So now you go up. So I think that's something that I actually have in the next slide. Yes. So now 14.8 is right here. So now if you look at the associated value of the gain, you see it's actually going to be somewhere around negative 44 dB. So that gain right here is actually going to negative 44 dB. So now that just tells you that in order to push this up so that this point intersects with the 0 dB line, you actually need to push this up by 44 dB, which is actually going to be equal to 162. Well, I mean the gain of 162 in decimal. So now basically you have to take that 162 and multiply it by that value of gain k that you actually started with in order to draw your body plot, which was 3.6, and it will actually give you 583.9. So now one very important thing to notice here is that if you had started with a gain k equal to 1 in order to draw your body plot, if instead, because what you see here, it was a body plot for k equal to 3.6, and again remember, this is actually the body plot of kg of s. This is not the body plot of the whole closed loop system transfer function. This is just the body plot of the open loop transfer function, which is, so this is really the body plot of kg of s. Okay. So now, like I said, if instead of k equal to 3.6, if you had started with k equal to 1, then here the final value of the gain that should have been adjusted would be exactly this value, 583.9. So now if you just go back to the original transfer function, which was this, so now you just have to replace the k by 583 whatever 0.9, and so then your final g of s which is going to be now, so now this is going to be your modified open loop transfer function is going to be what you see here. So now if you just take this as your new open loop system transfer function, you just put it in a unity feedback configuration, and you just plug and you just give a step input, then the percentage of overshoot, although you had actually designed for it to be 9.5%, if the actual value that after you do the simulation, you're actually going to get close to 10%, which is actually very close. So there's like only 5% error, which is actually pretty good. So now, and if you look at in the proposed specification, this percentage of overshoot would translate to 59.2 degree. That's exactly what we had obtained. And if you look at the actual value, if you look at the body plot of this G of S, it would be 59.2 degrees, which are actually exactly the same. So this really shows you if you're going to improve the transient response by adjusting the percentage of overshoot, all you need to do is just to change the gain K, and basically that gain K can just simply serve as a proportional control. So really what we have done is just to show you how to design a very simple proportional controller, and that design is actually going to be frequency design based, and it's going to be model based control design approach, and that's something that we have actually discussed so far in this lecture. Okay, so the next part of the design via frequency response is actually devoted to the design of lag compensator or lag controller, lead controllers, and lag/lead controller or compensator. So now first, I'm actually going to show you a general configuration of when and how you're going to add a compensator. So really when we talk about compensator, we often also refer to it as a controller. So now when we talk about designing a controller, it basically means designing a compensator. So now what does that mean? So now let's just assume that you have a system G of S, which is your open loop system, and you somehow want to improve the transient of the closed loop system by designing a controller. So, and again, we can design what is called stabilizing controller, meaning that your open loop system G of S is unstable, but you want to somehow stabilize it by designing any type of controller, a proportional controller, or even or any other advanced type of controller, like in the form of transfer functions. But in either case, what you have to do, you have to just add something like block here, and then you have to close the loop. So a lot of things that we have so far discussed, like adjusting the gains and finding the range of the gain case so that the system remains stable. And the first part of this lecture, I actually talk about improving transient response by just adjusting the gain. So really, I had a block here that was just simply a gain K, but then instead of a gain, I can even have here a transfer function. Let's just call that GC of S. So now this GC really represents a transfer function associated with another LTI system, which you're actually going to add to this open loop system. So now this GC is actually what is called, well, what we call a controller or a compensator. So now previously we just had the G that we had to work with, and when I added a gain, we had to actually look at the behavior of KG of S, either body plot, either the root locus, etc., or even the Nyquist plot. But now, instead of just the gain K, I'm actually going to make that like a dynamic systems just by adding a transfer function. So now you're going to add this compensator with transfer function GC. So now your open loop transfer function instead of G now becomes GC multiplied by G, and you now want to basically design your GC so that your GC multiplied by G meets the design specifications or behave the way that you want. So now the first type of compensator that I'm going to just briefly introduce today, but I'm not really going to discuss how to design this kind of compensator until next week, is actually what we call a lag compensator. So now, what is a lag compensator and when do we use it? So now we use a lag compensator when we want to improve the static error constant without resulting in any stability of the closed loop system. So the lag compensator can increase the phase margin to result in a desired transient response. So now basically, whenever you want to increase the phase margin, and remember, you always want to, so a good system always has a larger phase margin, which means that you actually further away from that point of instability. So you really want to be as far as, well, as further as yeah, so as far as possible to that negative 180 degrees phase line. So, and again, you can do that by adding a lag compensator. So if you say, so let's say if your system is only has like 5 degrees phase margin, and you want to boost that phase margin from 5 degrees to 50 degrees, what you do, you just have to add a lag compensator. So now here you see an illustrative example. So this one that you see, so this is actually, well, yeah, so I'm sorry. So this one that you see, that's the body plot of an uncompensated system, and that's the magnitude plot, and that is the phase plot. So now, as you see, looks like the open loop system here is unstable. Why? Because if you just look at the negative 180 degrees line, it's actually going to happen at this frequency. At this frequency, the body plot is actually above, the magnitude is above the 0 dB line, which means that really your gain K, well, your not gain K, your gain margin is going to be 0 minus whatever this number is, so it's going to be a negative number. Whenever your gain margin is a negative number, then that means that your closed loop system is going to be, well, is unstable. So now the question is, how do you then stabilize the system? So now basically, if you add a lag compensator, so the lag compensator, so the body plot of the lag compensator itself, it actually looks like this. So at very low frequencies, the magnitude is almost 0 dB, and it's going to drop, and at high frequency, it actually gives you a negative in terms of dB magnitude. Okay, and also the phase margin looks like this. So you so initially it's 0, it's going to drop, it's going to be here, and then eventually it's going to go up, and it's going to go to 0 again. So now that's the phase plot of a basically a lag compensator. So and again, basically with this type of lag compensator, your uncompensated system now is actually going to look like this. So now what you do, you have actually pushed without changing the without changing the low frequency response, or the low frequency portion of your response, both in the magnitude and also the phase plot, you have pushed down by this much your magnitude plot. So in that case, you see still at negative 180 degrees. Now you're actually going to be here, which gives you a positive gain margin, which means that your closed loop system is going to be stable. So now in general, if you want to know what form of transfer function a lag compensator or a lag controller will take, it's actually going to be something like this. So now as you see, so basically it's always going to be in the form of, let's say, s plus 1 over t divided by s plus 1 over alpha t. So it always has a pole and has a 0. So your pole is at negative 1 over t, and your 0 is at -1 over alpha t. So the thing here is that t is a positive number, but alpha must be greater than 1. So if you really want to plot the location of the poles and zeros on a PZ map, or in the S plot, it's actually going, or S plane, it's actually going to look like this. So if this is your 0, which is at -1 over t, then your pole is at -1 over alpha t. Since alpha is greater than 1, then that means that it's like -1 over 2t, 3, etc. So it's actually going to sit somewhere between 0 and the pole. So it's going to be somewhere here. So now always remember, for a lag compensator, your pole is always sitting between the origin and the 0. Okay, so now that's always how, and then later when I talk about the lead compensator, you're actually going to see that for lead compensator, your 0 is going to sit between your origin, well, between the origin and the pole. But for now, lag compensator, the 0 is actually further away from the j omega axis than the pole. So if you plot the body plot, it's actually going to kind of look like this. So at low frequency, it's almost like 20 dBs, and it's going to start to drop. And again, what you see is just a very typical, and of course, your body plot is just going to be dependent on the value of alpha and t. And I believe, yeah. So for this one, for this transfer function that you see, well, I mean the body plot that you see here, that's actually the body plot associated with these transfer functions. So that's s plus 0.1 divided by s plus 0.01. So now this is the lag controller, and this is going to be the body plot magnitude and the phase angle associated with these lag compensators. So the next thing I'm actually going to discuss is then how do we then select these two values of alpha and t to be able to design this very simple type of controller or compensator. So believe it or not, although this structure for the controller for a compensator is just fairly simple, because you just have a pole and a 0, a lot of times it actually works pretty well a lot of times. But again, just depends on exactly what your design specifications are. When you need to somehow improve the transient response by increasing or rather by decreasing the value of overshooting, by improving the value of phase margin, the type of controller that you need is just going to be a lag compensator. So in this lecture, I'm not really going to discuss how to design the lag compensator. In the next lecture, I'm actually going to show you a very simple design procedure on how to design this lag compensator, meaning how to tune this value of alpha and t to be able to get your closed-loop system response behave the way that you want. And of course, after that, I'm going to repeat that for the design of a lag compensator. And after that, finally, I'm going to discuss how to design or how to combine the design of a lag and a lead compensator, because sometimes you need transient response specifications that can be met or can be achieved using a lag but not using a lead. So some specifications can be met using a lead but not a lag, but sometimes you really need a combination of all that. So now in order to do that, you actually have to combine the two, meaning that you're going to have to design one lead, one lag, and your final controller is just going to be, or final compensator is just going to be the product of those two. And that's something that we're going to discuss in the last few lectures.